let's continue to the third part of mass spectrometry. So after this part, you'll be able to answer a few questions. What are the positive and negative ion modes of electrospray? Why are there multiply charged ions in electrospray? How to do nano electrospray? And what can we use electrospray mass spec for? So first, let's introduce what is ESI, Electrospray Ionization. So this ESI source consists of a very fine needle, like a capillary, just like you see, even finer. We need a fine opening because we have this orifice, and to the high pressure, when it shoots out, right, it will be generating a lot of aerosol. And because these liquids are charged, so they're compressed in a very thin needle into capillary, right? And you have this series of schemas. So once you inject out, right, they will form droplets, and this is what we want. When this drop carry the charge, once they exceed the capillary, and then it vaporize. So now we have a very highly charged analyte. So ESI is especially very useful for large biomolecules like your proteins, so hard to vaporize or ionize. Here's a schematic diagram. So of course we are blowing this up, but imagine a capillary, it's so thin and fine, but you expand it, so inside contains your charged species, right? And then we try to evaporate to concentrate it, and then when you shoot out, you fragment into its own individually charged ions, leaving the droplet. And here you have a detection. So for ESI, the sample is typically dissolved in a polar and volatile buffer. Why? Because we want to vaporize it. If it's not volatile, you can't vaporize easily when it's wet. Wetness also absorbs charge. No salt, because ionic salt has this Coulombic attraction that makes it very hard to vaporize. The raw pumped through a stainless steel capillary. This is the diameter at a rate of 10 to 100 microliter per minute. And a strong voltage of 3 to 4 kilovolt applied to the tip, just like you see, right? With a flow of nebulizing gas to cause it to nebulize. To nebulize something means to form aerosol, to aerosolize. So this is like the spray. They find, around, let's see. You see the spray, right there, it's a very fine droplets. So fine that so many goes to my eyes. But it's very refreshing. So this aerosol is directed through the region of a high vacuum until these droplets evaporate to near atomic size. And they still carry charge, because if they are not charged, we can't detect it through mass spectrometry. Now how can we modify into a nanospray system with a flow of less than 1 microliter per minute? And because it's so precise and fine, it's highly sensitive, and therefore you need less than a picomole of the material. And of course, when it's so small, it's highly affected by the little presence of salt and detergent. Because again, we want to make it very little and make sure that all the solvent has dried up. So when you have very minute bit of salt, it's not helpful. We have two kinds of modes. One is the positive ion mode. It measures the N plus H plus, right? So we add some acid to solvate it. We also have the negative mode, negative ion mode, which is the N plus H minus, and we add the base ammonia to solvate it. Now, how to choose which mode to use, the positive or negative? We look at the sample. It's all about the sample. First, we look at the structure and see, or we know that if it has a functional group that's readily accepting H+, which means it has some kind of a nitrogen in the form of amine amino group, peptides, proteins, then we'll apply the positive ion. If the sample has functional group that's able to detach a proton, like carboxylic acids or hydroxyl group, like your DNA, nucleic acids, sugar, then we apply the negative detection. So therefore, I want to iterate, it's so important to apply your organic chemistry in terms of structural recognitions, the functional group, what they are in this molecule. Another diagram of ESI here, right? So you see this ESI needle, spray and dispart solvent vaporization becomes smaller, charge repulsion, split, ion evaporation, further, concentrate, and analyze. Here, I want to show you another picture. Maybe it's a bit better, it's more colorful. When you have a large droplet here, right? So within this droplet, there's different kind of charges. But to make sure they can split into smaller charge, we need to lower the volume. Because lowering the volume means you are bringing the charge closer. We know that the Coulombic attraction and repulsion is also dependent on the distance. So if you're able to bring them closer, you experience more repulsion. So what we want is the Coulombic explosion, when the charge is so near that they repel and goes away and split, and therefore splitting into very fine small ions. And this is what we want, very tiny ions. Something called the API in mass spectrometry, the atmospheric pressure ionization. The energy comes from this atmospheric pressure ionization is lower than that in GCMS. Okay? We do this for a purpose, because you saw that for big molecule, right, some of these mass spectra, they are very, very complex. But if the energy is lower, you can't split so much, so you don't chop and cut so finely, then your spectra become simpler, but simpler for a good reason. Because when you have, let's say, a big picture and you cut too many pieces, you can't piece them together, just so confusing and cumbersome. But what you want is to get a general picture first. For certain molecules to affirm its structure, I think API is good enough. So some of these API modes include the ESI, the APCI, atmospheric pressure chemical ionization, APPI, atmospheric pressure photoionization. And for ESI-MS, regardless of what ionization mode, always prefer to use volatile mobile phase additive. Again, the same reason. We want to lower the volume so that the charge comes closer and repel to become smaller. Okay? What are these volatile additives? Formic acetic acid. Recall that to bring a proton, right, to make it a positive mode, we need to have a source of proton. So we can typically choose any organic acid, but notice here we are choosing the 1 carbon 2 carbon acid, because the lower the carbon chain, the lower its boiling point, the higher the volatility, which serve our purpose. Of course, you can use your dodexyl acid, but it's not volatile. So you can use it as a proton donor, but it's not good for MS because it doesn't dry away. For the basic side, we can use ammonia or triethylamine. Right. For something in the middle, we can have ammonium formate or ammonium acetate. More like a buffer, like a weak base plus a weak acid together. Here is how it looks like for the nebulizer, the spray. So here we have just a spray, right? You can't see the orifice, the hole. One more time, because it's refreshing. Can you hear the sound, by the way? Okay, the spray, right? So when you see this, the right side, here's what happens here in slow motion, right? If you can see. Okay, a very small, tiny hole opening. Question for you. Do you think it's charged? This droplet? Thermal spring water, is it charged? You can file at home. So, in this case, you see on the same picture, two examples. One's using a positive ion mode, which means we are applying acidic medium. So your sample, reaction with an acid, you form a M plus H plus. In the other side, in the basic medium, pH more than 7, you have a M minus H minus. It loses H plus. Okay. Another picture. So again, this is non-colored because if you're asked to sketch it out, I think you should be able to draw a schematic diagram, the different parts of what constitute the electrospray, right? Where the schema is, where's the capillary, where does the nebulizer comes about, and where does the aerosol gets ejected. So this ESI is produced by applying a strong electric field. Okay. Under API, to a liquid passing through the very thin, very fine capillary with a weak flux. Then we have this electric field obtained by having a potential difference 3 to 6 kilovolt between the capillary and the counter electrode. Okay, and then we separate it by a bit of space, 0.3 to 2 cm, and it will produce electric field of millions, in the scale of millions, volt per meter. We have to have the capillary heated because if it's not heated, it will tend to aggregate together. So in a way, we're trying to preempt it to separate when it's exciting. It's like we can of course do a heating at the end before the nebulizer, but we want to preheat it up so that the energy, is getting it ready. When you have the exit, it just shoots out, coming from not just the charge repulsion, but inside it having enough kinetic energy. Here, what we want to find is the different parts within the ESI MS. Now, on the left, you see if we apply this at the low voltage, then the drop, the droplet, and the tip of the capillary is very spherical. This is similar to, you take a straw, a straw, then you just see a straw in the end, then you see the droplet is round. The centerpiece, when you apply some small voltage, 1 to 2 kilovolt, then you see there's a bit of tapering, like a V shape. Okay, and tend to elongate to the right as we have pressure accumulation. And on the right side, when you have a bit more higher voltage, then there's a pressure that's higher than the surface tension and tend to, eject and split, become very fine droplets. Okay, and therefore this is what we want, the spray. So in science, there's this principle called the Rayleigh limit, called Q. And above that, this Coulombic repulsion overcome the surface tension. We know that, when we have bubbles when you shower, the bubbles, when you put them together, tend to form bigger bubbles because of surface tension. They want to lower the surface tension always. The circumstance in the water side, we want to lower surface tension because surface tension incur energy. But there's a counter effect here called the Coulombic repulsion. So let's say within the droplets, of course they tend to come together to form a whole bulk, bulk solution. But if they themselves are charged, the charge repulsion will cause them to split. So there's a tension that's grappling with, a struggle, a tension. So when the charge repulsion is more than the surface tension, you have this Coulombic explosion phenomenon. Just a formula for you to substitute if you're given such data. Now for multiply charged ions. So now you consider a positively charged ion with Z1, and the MZ ratio is measured to be M1 Thomson DH, issued from a molecular ion of mass capital M Dalton. The 1 Dalton is 1 AMU, atomic mass unit, into which Z1 protons have been added. Then we have this formula where the product of the protons and its mass is equals to this mass of the molecular ion plus Z1 multiplied by MP. Here's the mass of the proton, and mass of a proton you also can express in the form of an AMU. So an ion, which is separated from the first one, because they fragment, we call the J-1 peak. We can also measure its MZ value ratio, M2 Thomson, and the number of these charges, the Z1 minus J. So we can also find the decrease in mass via this formula. Now consider two cases. One for the positive ions. So when you do a substitution inside, the two equations will give rise and simplify into these, in blue. And for the case of the negative ion, it will simplify into the last line. So the main difference if you observe is that the sign here, for the positive ion, this is negative, For the negative ion, this is positive, and that's the only difference. How does sensitivity of ESI-MS relate to concentration of the sample? Okay. Now, what you have to know is the sensitivity of ESI is correlated to the concentration, not the amount. Not the amount, not say I have a high volume, right, of the low concentration of the sample. Because you know we have a high volume of a low concentration, your number of moles could be very large, but that doesn't increase the sensitivity. It's about the concentration. Therefore, you link back to why we choose volatile solvent, why we choose formic acid or acetic acid over propanoic acid, for instance. How do we achieve this higher ion intensity? Right here, you see, we want the peak to be narrower, higher, okay, more sensitive. So you can see that, right, in this case, HPLC, okay, on a 2.1 mm column, 400 microliter per minute flow, okay, and the drugs are analyzed. So on the left, this is the flow rate, center, slower flow rate, right side, even slower flow rate. Okay. What do you see? Okay, this is another possible question you'll be asked. In terms of the splitting, the distance between. You notice first that the time taken is the same, right? There's no difference between the time taken for them to renew. Number two is this increment, right, of the signals, just marginally. So of course you can see that by reducing this flow rate, right, we do have a slight increment in the ion intensity. Okay? And at reduced flow rate, the sensitivity did not decrease the same concentration. Okay? So here we have different kinds of sprayers for ESI, just like different tools to make an electrospray. For A, the first part is a pure electrospray, where you have a sample solution here, the more simplistic one, okay, just split. So this is good for 1 to 2 microliter per minute and for slow flow rate. Next, we have something a bit more complex because of engineering. We begin with pure electrospray and then we see how can we better it with high technology. One is using a shield liquid within. Okay, there's a shield in the internal layer, and then we inject the sample solution within, and you see that it's longer, it can spin to finer spray. This is for CMS, capillary electrophoresis MS. See the one you learned before. Okay. It does provide some electrical contact, because C also you encounter some form of potential difference. Next, we have the Pneumatically Assisted Esi, where we have the assistance of a nebulizing gas, within here, simple solution within, and the solution flow rate, as such, good for LCMS, liquid chromatography, mass spectrometry. The last one is very powerful. It's called ultrasonic nebulizer. We have something bigger with the incorporation of this auxiliary gas from a side, sample solution, and the key element here is your ultrasonic transducer using kind of wave, okay, to help to propagate, vibrate it. And here we have what we call the longitudinal vibration using the ultrasonic wave, right? So you excite the molecule in the solutions, and once it comes out, split. So it does tolerate a high conductivity and high surface tension. Okay. Besides using different kind of electrospray, we can also adopt some strategies in commercial atmospheric pressure ionization ion source. So there are some commercial brand in the industrial lab. You don't just say, okay, you look at the name of the brand, right? Say, oh, Pepperpot, Crossflow, LCZ, yeah, micromass, AQA. So either we use the name of the company or we just use the name of this series of Electrospray.